Okay. Here's like a warm-up problem. Why don't you pause the video and see if you can figure this out. So if you want to figure this out, one of the things that you might think about is that, well, obviously the first thing that you have to do is you have to balance the equation. Okay, so I'm going to start out with a 25 in front of the carbon because of that 25. And for the hydrogen, I'm going to take 52 divided by 2, which is 26. Okay, and then I'll know that I have 50 oxygens plus 26 oxygens is 76. And if I take that and I divide it by 2, I'm going to get 38. So I need 38 oxygens. So if I burn 2 molecules of paraffin, how many molecules of CO2 would I produce? Well, I know that if I burn 1 molecule of paraffin, I'll make 25 molecules CO2. Okay, so if I just multiply everything by 2, then I get 2 molecules C25H52 yields 50 molecules CO2. Now, notice that I can make an equality out of this. And I'm going to choose to keep working with this one. Okay, I can say 1 molecule paraffin equals 25 molecules CO2. All right. Now, I want you to convince yourself that if you multiply both sides of this by 2, you'll get this, and that'll be true. Now, if I multiply both sides by 3, it'll still be true. So I can multiply both sides by any number. So why don't I multiply it by something crazy, like 6.022 times 10 to the 23rd? As long as I multiply it on both sides, it's still true. Now, watch what happens when I do this. I'm going to multiply both sides by 6.022 times 10 to the 23rd, and then I'm going to convert molecules into moles. Okay? So I'm going to write a little smaller here. 1 molecule C25H52 times 6.022 times 10 to the 23rd. And then I'm going to convert that into moles. So I want moles of C25H52, and I'm going to use Avogadro's number on bottom, 6.022 times 10 to the 23rd molecules C25H52. Okay, and this equals, I'm going to scroll down, I'm going to use the bottom here, 25 molecules CO2 times 6.022 times 10 to the 23rd, and multiply by 1 mole CO2 over 6.022 times 10 to the 23rd molecules CO2. Okay, so let's go back up and let's try to simplify a little bit. Okay, my molecule cancels out. My molecule of C25H52. Gotta be careful about labels now. Okay, and look, hey, this number cancels with this number. So all I'm left with is 1 times 1. So 1 mole C25H52 equals, let's do the same thing down here. Cancel out molecule CO2. Cancel out my 6.022 times 10 to the 23rd. And I can say 25 times 1, 25 moles CO2. Whoa, whoa, whoa. Crazy, right? Now, so that means that these numbers are really ratios between moles, and we actually call them mole ratios. It's one of the only things that we have correct names for. Okay, so based on this, could I write any more mole ratios? Sure, I can write as many as you want. Let's just do 2 more, just to prove my point. Okay, I could say 1 mole C25H52 equals 38 moles O2. Okay, so now I just did the relationship between the C25H52 and the oxygen. Okay, I could also do 38 moles oxygen equals 26 moles of water. Okay, so I could write mole ratios for anything in a balanced chemical equation. Okay, so this is actually very helpful for us. So one of the things that we can do here is we can convert from moles of a known compound to moles of an unknown compound. Okay, and the conversion factor that we're going to use here is, of course, mole ratio. Okay, so let's see an example problem. Burning ammonia in the presence of excess oxygen produces nitrogen monoxide and water. How many moles of NH3 are needed to form 9 moles H2O? Now, one of the important things to understand is what this term excess means. Okay, for now, what excess means is you just have more of it than you need. Okay, you have more oxygen than you need, so you can ignore it. Okay, that's not going to be true later in the unit, but for now, we're going to call that, we're just going to say ignore anything that you see as an excess. Okay, so obviously now the first thing that we need to do is to make the balanced equation. That is always the case. So I've got burning ammonia in the presence of oxygen yields nitrogen monoxide plus water. Okay, so now I can go back and balance this. The first thing that I see is an odd even disagreement with the hydrogens, so I'll fix that first. Okay, so now I need 2 nitrogens with the 2 nitrogens here, I've got 6 hydrogens here and 6 hydrogens here. So I've got 2 and 3, 5 oxygens. So the only way that I could get this is with 5 halves, which means we're just multiplying everything by 2. So that's 4, that goes away, that's 4, and that's 6. Okay, now I just have a straightforward dimensional analysis problem. How many moles NH3 equals, okay, so that's my unknown, moles NH3, and then my known is this 9 moles H2O, okay, 9.0 moles H2O. Okay, now I'm going to start my conversion factor. I'm going to put moles H2O on the bottom. And then I'm able to go straight from moles of H2O to moles of NH3. No problem. Okay, so that's 6 moles H2O to 4 moles NH3. Now, some of you might be wondering why I don't simplify and just do 2/3 here. Okay, it's important to write these numbers out properly first. Then you can go back and you can make changes. Okay, so then I can do my, well, I know that this is a 2 and this is a 3. So 9 divided by 3 is 3, times 2 is 6. So my answer is going to be 6.0 moles NH3. Okay, and that's really it. Now I'm going to give some sample problems that get more difficult, and make sure that you try the problem before you see me work it out on the video.